Hi, my name is Leon Starr, and these animations go with my article titled Time and Synchronization in Executable UML. You can locate the full article at www.modelint.com. We want to deliver our models on an unknown and evolving configuration of processing units, such as CPUs, threads, tasks, whatever. So we can't rely on a single global clock to resolve all our synchronization problems. In fact, we will ensure that our models synchronize correctly on a worst-case distribution. Here we see that each object has its own local clock. In fact, this sets the stage for the rest of our synchronization rules. We can't rely on a definitive processing speed to synchronize our models. So each state's procedure will require some unknown amount of time to execute. Here's a state in a model we are testing on a relatively powerful desktop simulation environment. This procedure executes very quickly, but in a resource-starved embedded processor environment, it takes considerably longer for the same procedure to finish. Events do not interrupt busy objects. Since events are never lost, they must be held for later processing if the addressed object is busy. Here, a door object enters the open delay state and begins executing its procedure. While this is going on, two events occur. Since the object is busy, both events are held for future processing. These events are not necessarily queued. When the procedure has completed, the door object is presented with one of the held events. Notice that the object doesn't get to choose the event. The state table is then consulted to determine that this state offers a transition for that event, and then the door object follows the indicated transition. The remaining event is held so that the door object can process it in some future state. If there are no pending events, the object will just wait in the current state until the next event occurs. Here, the door object waits until the time to close event arrives, triggering the transition. The model architecture guarantees that each generated signal is delivered to its recipient as a corresponding event, and the models must be able to process any event that occurs regardless of the current state. When an event occurs, an object can process it in one of three ways. The object can follow a transition, the object can just ignore the event, or an error is declared. Let's take a look at an example of each case. Normally, we expect an event to trigger a transition to either a different state or possibly back into the same state. Here, two door objects are waiting in the open delay state. The time to close event occurs for one of the doors. The table for this state chart is consulted to determine the appropriate response when this event occurs in the current state. Since a destination state is specified, closing in this case, we know that there is an exiting transition. This transition is drawn on the state chart. As the object exits, the processed event is destroyed. If we are in a state where no action is necessary, either now or in the future, an event can be safely ignored. Here we have an object waiting with the doors open. Someone in the cabin pushes the open button, but the doors are already open and there's nothing for us to do. So we specify ignore as the response in the state transition table. The event is discarded and the door object remains in the open delay state waiting for the next event. Keep in mind that ignoring an event is just as normal as transitioning. And if all you need to do in response to an event is to store some data for future reference, this is best handled synchronously with the method or domain function instead of complicating your state charts. To build safety-critical systems, you have to consider the occurrence of any event in the current state, not just the ones you are expecting. When it is time to close the doors, or a passenger pushes the close button, we enter the holding open state and check to see if the open button is being pressed. Our example door object finds that the open button is being held, so it sits in this state waiting for a passenger release event. Well, that's odd. The time to close event unexpectedly occurs. Since the expiration of the open time delay gets us into this state, and the initiation of this delay is triggered in a different state, it should be impossible for the time to close event to happen here. Consequently, the table entry designates the error response. The error response will trigger whatever system-level recovery behavior has been designed into the model virtual machine. The occurrence of an error generally causes us to go back and fix our models. Possibly we forgot to cancel the timer when the user hit the close button before the open period expired. Another more remote possibility is that the model virtual machine is not working correctly. When filling out a state table, always start with error as the default response in all the table cells. You actually want to force your models to crash so that you can detect and fix your design errors during development. Self-directed events are processed before any other events. The occurrence of an event is the only way for an object to exit the current state. But sometimes an object will perform a test or computation and decide that it wants to pursue a transition without waiting around. It does this by sending a signal to itself. In our example, a cabin object normally waits at a floor for passengers, but it always checks to see if its shaft is still in service. If not, the cabin will send the out-of-service signal to itself. This should result in a transition to an appropriate out-of-service state. But what would happen if a new transfer event occurred at the same time? Without our self-directed event rule, we could end up processing the new transfer and ignoring the fact that the shaft is out of service. Incoming events should not interfere with our choice to force a transition. Since an object always receives self-directed events before events from any other source, internal decisions won't be compromised. Let's see how this works in a worst-case example. A cabin enters the transferring passenger state and begins executing its procedure. While this is going on, a new transfer event arrives. The event is held, of course, since we are busy executing a procedure. The cabin sees its shaft is no longer in service, so it sends the out-of-service signal to itself. By the way, since this if/generate action has no data dependency on any of the other actions in the state, it may execute in parallel or even earlier than the other actions. You shouldn't assume that actions are processed in vertical order, though that's a topic for a future article on action execution. Anyway, the out-of-service signal is also held. Notice that the model virtual machine must distinguish between self and non-self-directed pending events. Now that the state procedure has completed, the cabin object is presented with a pending event. Even though it arrived later than the new transfer event, the out-of-service event is seen first because it is self-directed. So the cabin object takes the corresponding out-of-service transition to the out-of-order state. The very minimal state procedure is executed, and then the still pending new transfer event is received where it is ignored and discarded as determined by our state table. Order is guaranteed for signals originating from the same sender, but not from separate senders. This is a key consequence of giving each object its own local time frame. Here we have two senders, A and B, communicating with a recipient object R. The signals sent from A are guaranteed to arrive in order so that ignition occurs before launch on any platform. This is because we can use A's local clock to timestamp its signals. But whether the abort signal from B arrives before, after, or between the two signals from A is entirely platform dependent. This is because B could be running in an unsynchronized time frame. Ultimately, the application requirements will determine whether or not the relative signal timing between A and B needs to be coordinated. If we want to ensure that the signal from B always arrives, say, before the second signal from A on any platform, then the two senders would need to coordinate explicitly, not with hopeful timing, but with some interlocked configuration of events, states, or status attributes. One of the cool things about the execution rules is that there are hardly any rules at all. With them, you can test your models once and then change them only when the application requirements change, not the underlying platform technology or the task or processor distribution. You can imagine the benefit, especially if you have invested considerable resources modeling large, complex domains. Let's summarize the rules. First, there is no global clock. So we assume the worst-case distribution where each object is running in its own local time frame. It is unlikely that the models will be targeted at such an extreme distribution, but if they work under these circumstances, they should work anywhere. 2. Procedures have unknown duration. The amount of time it takes for a procedure to execute is platform dependent. Execution may be quick, but it is never instantaneous. 3. Events do not interrupt busy objects. Since you cannot use an event to interrupt a procedure, you should break down your states to define the granularity of interruption relevant to the domain you are modeling. 4. Signals are never lost. We're talking about signals internal to our system, of course. All events received by an object will result in a transition, ignore, or error response. Self-directed events are always seen before any non-self-directed events. And finally, 6. Signal order from a single sender is preserved. For more books, articles, training, and assistance with Executable UML on real-time and embedded applications, please visit our website. Feel free to email any comments or requests to me directly, Leon_Starr@modelint.com.